Hello everyone, welcome back to From Brute to Best. In this video, we are going to talk about greedy algorithms. Greedy algorithms look simple, they look efficient, and very often they look correct. But today, I'll show you why greedy algorithms silently fail, even when they pass sample test cases, and even when the logic feels completely right. If you have ever thought, my solution makes sense, why is it wrong? This video is for you. First, let's quickly clarify what greedy really means. A greedy algorithm makes a local optimal choice, hoping it will lead to a global optimal solution. It does not backtrack. It does not reconsider earlier decisions. Once a choice is made, it is locked. And that single property, locking decisions early, is where most greedy failures come from. Trap number one: local best does not guarantee global best. Greedy sees the best option right now, but it cannot see how that choice affects future possibilities. This is why greedy fails in problems like job sequencing, interval selection with weights, and certain scheduling problems. The first decision looks perfect, but it blocks a better long term solution. I would like to give you an example of trap 1. Let us consider this problem. We have a set of coin denominations and a target amount. We need to find the minimum number of coins needed to make the amount. Let's say we have 1, 3, and 4 as coin denominations, and our target amount is 6. We have to find the minimum number of coins needed to make 6 using 1, 3, and 4 denominations coins. So, we can make 6 in the following ways. Way 1, using 1 6 times, used total of 6 coins. Way 2, using 1 2 times and 4 1 time, used total of 3 coins. Way 3, using 1 3 times and 3 1 time, used total of 4 coins. Way 4, using 3 2 times, used total of 2 coins. Out of all these ways, the best is the way 4, where we used only 2 coins to achieve the target amount. I will show you 2 code examples, first with the wrong greedy approach, and second with the correct dynamic programming approach. Let me quickly write the code for greedy approach. I already have created this class greedy approach where I will write the code for with the wrong greedy approach solution. Okay, so let me quickly write the method definition here. Sorry. So this will be our method and it will take two parameters in the input. One is the array of coins and the target amount, right? Okay, now we will first sort the array. Okay, so we will use the arrays.sort function to sort it, and we will have a count variable initialized to 0. Now we will traverse through the array then we will
check for the amount with the coin. Let me add some sysalts.
The code I have completed here is a solution to our problem following the greedy approach. Here we are traversing the denominations from largest to smallest, checking if the remaining amount is greater than the denomination. If the remaining amount is greater, we are using the denomination. Later, we are subtracting the denomination from the amount and increasing the count. At the end, if the remaining amount is not equal to 0, it means the target amount is not achievable and we are returning -1. Otherwise, we are returning the count. Here, I have added a few prints to see the messages in the console. This will help to see us steps our program will follow. Let me quickly run the program. Here we are using the same test input as our example. Our denominations are 1, 3, 4, and target amount is 6. Our expectation is 2. Let me quickly run this test. As you can see, our program returned 3 as output, where our expectation is 2, and that's why our test status is fail. I will tell you why this greedy approach is wrong. Greedy picks 4 first. The remaining amount is 2, forced to use 1 2 times. So, the total coins used is 3, but optimal solution should be using 3 2 times. Now, let me quickly show you the correct approach. I will build the solution using bottom-up approach and reuse previous answers. To save some time, I have already created a class for this. I will simply write the code for the solution. Please be with me while I complete the code.
So this is our method, which will basically contain the code of the dynamic programming solution for the problem. Now here, so this method also, as you can see, it has two parameters. One is the array of coins and second is the target amount. Now let me quickly write the code here. I will explain the code later, don't worry. So I will just initialize a value with this array using our arrays.fill method. Okay, so let me add few comments here just to give you a heads up or make you understand it easily. Okay, okay, fine. Now I will set the first index value to 0. I will also add some sysouts just to see logs on the console. If L is greater than equals to coin, if the amount is greater than equals to coin, then just let me print a message here that we are using this coin. Yeah, so we will simply calculate the number of coins for this amount from the previous step. So whichever is minimum between current step and previous step, we will take that value. So this step, and let me add one more this out. Sorry. Just let me keep this message bit understandable. Instead of if else check, let me just use a ternary operator quickly. Okay.
The code is completed for the second correct approach. At the beginning, I am creating an array to store the result of each step. I am calculating the number of coins for each amount, starting from 1 up to the target amount. Then we are traversing through all the denominations and calculating the number of coins to be used for that amount. If the coin is usable for the amount, we are comparing the number of coins from the previous step and using the minimum of it. If the number of coins used for the previous amount plus 1 coin for this step is less than the number of coins for the current amount, we will use the number of coins from the previous step. Otherwise, we will keep the number of coins from this step only. Here, we are using the same input for testing. Now, let me quickly run the code and see the result. As you can see, the output is 2, hence the test status is pass. As you can see in the console, the code is calculating the number of coins for each amount and storing it inside the array dp. For each step, the code is comparing the result with the previous step's value and using the best value for that step. Trap number 2. The sorting order decides correctness. Many greedy algorithms depend on sorting. Sort by start time instead of end time? Wrong answer. Sort by value instead of ratio? Wrong answer. Greedy is extremely sensitive to ordering. One wrong comparator and the entire solution collapses. Let me show you the example in our code. In our code number 1, the greedy approach, we were sorting the coins array and traversing from largest to smallest. But if I use the wrong order here, the same logic will give us a different result. Let me quickly change the order and show you. Here, I will use the stream API to sort the coins array in descending order. I hope you are aware of Java Stream API. If not, please mention this in the comment. I will prepare a separate video on Java Stream API. Here, I have changed the sorting order. Now the coins array will be sorted in descending order. If we run the code with the same test data, you will see a different result in the console. As you can see, the result is now showing as 6. Now, if we remove the sorting step and rerun the program, we will see a different output. I have commented the code for sorting. Now, let me quickly run the test. As you can see, this time the code has returned a different value. At the end, I hope you have clearly understood that the result using the greedy approach depends on the sorting order of the input array. Trap number 3 is the most dangerous one. Passing sample test cases. Greedy solutions often pass small inputs. They fail only on carefully crafted edge cases. That creates a false sense of confidence. You submit and suddenly, wrong answer. This is why greedy must always be mathematically justified, not emotionally trusted. Let me give you an example. Suppose we have a list of intervals. We need to find the count of the maximum intervals from that list. On the left of the screen, I have the code solution using the wrong greedy approach. Here, I am sorting the intervals based on the difference between their respective start and end timings. Then, I am finding the maximum intervals if the start time of any interval is within the last end time. And on the right side of the screen, I have the code solution using the correct approach. In the correct approach, I have a small change in the sorting. Instead of comparing the intervals based on the size of the interval, I am sorting by comparing the end time of each interval. Now, let me show you the test input data. Here, I am using intervals as 2, 3, 4, 5, and 6, 7. My expectation is our program should return 3. I am using the same input for both the codes. Let me run the program in both sides. As you can see, both codes return the correct result and the test status is pass. This gives the impression that the code is correct in both places because both of our codes return the expected result correctly. Let me quickly change the test data. Now, I will use the intervals as 1, 4, 2, 6, 4, 7, and 6, 8. Using these intervals, our code should return 2 as the count of maximum intervals for the intervals 1, 4, and 4, 7. Let me run the code on both sides. As you see now, the test status on the left, using the wrong code approach, is fail. The test status on the right, using the correct code approach, is pass. This shows that even though the wrong approach code passes for a few inputs, but it may fail for some edge cases. Trap number 4. Early commitment destroys flexibility. Greedy algorithms commit early. If the problem requires future context, greedy is already in danger. Problems involving future constraints, dependencies, or delayed rewards usually punish greedy solutions. For trap number 4, consider our first problem, where I wrote the code to find the count of the coins to reach the target amount. The wrong approach failed because it committed very early to the problem and locked the decision too early. That's why it returned the incorrect result, even though an optimal solution was still available. Whereas in the correct approach, it is finding the optimal solution for all the amounts using current and previous data. That's why it was able to find the best result. This is a classic example of trap number 4. Now, an important question. When does greedy actually work? Greedy works when local optimal choice always leads to global optimal. Decisions don't affect future choices negatively. Problem has optimal substructure. Classic examples include activity selection, Huffman encoding, and certain interval problems. Before using greedy, ask yourself, can an early decision block better future options? Does ordering matter more than I think? Am I proving correctness or just hoping? If you can't clearly justify greedy, it's probably the wrong approach. If this video helped you understand greedy algorithms better, please like the video. It really helps the channel. Share this with someone who's struggling with algorithms. And don't forget to subscribe to From Brute to Best for deep, practical algorithm explanations. If you have any doubts or want me to make a video on a specific algorithm or problem, drop it in the comments. I read every single one.